right, so right now we're going to talk about an overview of the buffers. This will be a little bit of a review, so you may or may not need this. So the first thing that you need to remember is that the buffers maintain the pH with the addition of a small amount of strong acid or strong base. So for example, so we maintain pH. So if we had a solution here that was an actual buffer, and we put into that buffer, let's say 1 mil of 1 molar HCl, then the pH shouldn't change. So if the original pH of this is, say, 4.5, after we have the addition, so I'm going to put that in red, so now we've got this addition here, then the pH after should be close to 4.5. Now, let's say we don't have a buffer. We have just water. Water is not a buffer. And now instead, we put in there 1 mil of a 1 molar hydrochloric solution, so our strong acid. The original pH, let's say, is 7 because it's neutral, just water. And then what you're going to notice is that the pH after should change drastically, and the pH afterwards for this ends up being, instead of 7, which is the original, it might be 2.0. Now see, that's a drastic change, so our water is not a buffer solution, but up here we don't see a drastic change, and so it maintained the pH, and that's what a buffer does. So the requirements of a buffer is that you have a weak acid conjugate base or a weak base conjugate acid. Now remember, for example, if we have acetic acid, which we know as a weak acid, if you didn't know that, you would look up Ka, and you would notice that your Ka is low, times 10 to the negative something. I think for acetic acid it's 1.8 times 10 to the negative fifth. And if we look at that, its conjugate is going to be 1 hydrogen different because it would donate its hydrogen, and so we would have our acetate. So notice here we've got the change between those two. So we have acetic acid, and remember they have to be on opposite sides, the conjugate acid base. So over here we have our weak acid, and here it's its conjugate base. Those are always going to be on opposite sides of the equation. So we have our double arrow because we have a weak acid dissociating in water, and then we need to have our hydronium ion plus acetate. So here we have a potential buffer. Now the second thing you have to have is that you need concentrations of both. So we would need, say, 1 molar of the weak acid and maybe 1 molar of the conjugate base. So you need concentrations of both. So now we know that a buffer maintains a pH with a small addition of strong acid or strong base, and that an actual buffer to identify it is a weak acid conjugate base or weak base conjugate acid pair, and we have to have concentrations of both. So for example, acetic acid and acetate, which we just talked about, is a potential buffer. We just need concentrations of both of those. So now let's look at this. This is practice problem number 1 in your in-class sheets. And you'll notice from this problem, it wants to know, can this mixture be considered a buffer? So what do we look for? We look for a weak acid conjugate base or a weak base conjugate acid. And when we look at this, we're going to see what do we have, and we're going to go through, we have acetic acid, which we know to be a weak acid. And then we've got sodium acetate. Here's my acetate, and we know that to be the conjugate base of that weak acid. Now notice a number of people will ask about this sodium. Why? What happened to it? Well, it's a spectator. If you remember your solubility rules, if you look at that sheet, you'll notice that under acetate that sodium acetate is soluble, so it completely disassociates. So if I put sodium acetate into water, it will completely break apart or ionize into sodium and acetate, and that's where we get that acetate from. So it's free in solution. And then notice, so we've got that part, we've got our weak acid conjugate base, and then the second requirement is, do we have a concentration of both? Now when we look at this, we have 1 mole of acetic acid in 1 liter, and we have 0.5 moles of acetate. So for our weak acid, which is our acetic acid, we have 1 molar. And for our conjugate base of that weak acid, we end up having 0.5 in 1 liter, and so we have 0.5 molar. So yes, we do have a buffer. Now the next part is, what is the pH of this solution at equilibrium? And I want you to do that before our next session. So that'll be our online session, and that'll be our in-class. So I want you to work this problem. So you got to find out now the pH of that solution. Now remember, it's a weak acid conjugate base. So you're going to start with your Ka equation because we need to be able to solve it that way. So you're going to start with your acetic acid, just thinking about it, plus water yields acetate plus H3O. Now you could set this equation up and do the whole ice chart and solve it. You can solve it that way and you will get the correct pH. But because we know that this is a buffer, you can also go straight to the Henderson-Hasselbalch equation. And that was given on your tool shed sheet, so make sure you look for that. So ice or Henderson-Hasselbalch equation. Now I vote for Henderson-Hasselbalch because it's a lot shorter to use. And that is how you identify a buffer.